Hello, welcome to our lesson on chapter 9, which deals with the representation of Boolean functions by formulas. In this chapter, we will present two normal forms of Boolean functions. In general, a normal form is just a restricted syntax for Boolean formulas. We already saw the negation normal form, which allows negations to be applied only to variables or constants. Today, we will consider two more normal forms. One is called disjunctive normal form, or DNF in short. And very often this form is also called sum of products, or SOP. The second normal form we will look at is the conjunctive normal form, also known as CNF, also called product of sums, or POS. Finally, we will also consider polynomials over finite fields. We'll get there. So, let's define what a literal is. A literal is simply a variable or a negation of a variable. For example, x is a literal, where x is a variable, and not x is a literal. A product or a conjunction is simply an AND of literals, and we require that the number of literals be at least 1. So the case that k equals 1 means that our product is just one literal. Otherwise, in the more general case, we will have a product of many literals. Now recall that we denote the AND connective either by a dot, like a product, or a upside down V. They are all the same logical connective in our eyes. And recall that AND is associative, and therefore when I write the expression L1 and L2 up to and LK, I need not write the parentheses because the Boolean function that corresponds to the AND connective is an associative function. Okay, so if you want to see an example of a product, this is a product, x and not y and z. And this product equals this product because I do not see any distinction between the AND connective and the dot here, the AND connective and the upside down V here. It's the same for us. Okay, so all these products are the same product. Good. So suppose I have a product P, and I can look at the set of variables that appear in V. And I can denote this set of variables that appear in P by vars of P. So for example, if P is the product x1 and not x2 and x3, then the set of variables that appear in P is x1, x2, and x3. Notice that x2 is a negated literal, not x2, is a negated literal in P, but x2 appears here without negation because it's a set of variables. Now, I can make a distinction between the variables that appear with a negation and those that appear without a negation in P. So let vars plus of P denote the set of variables that appear in P without negation. So vars plus of P here is x1 and x3 because x1 and x3 appear in P without negation. On the other hand, I can define vars minus of P to denote the set of variables that appear in P with negation. For example, in this P, x2 appears with negation, so vars minus of P is just the set that consists of x2. Finally, let literals of P denote the set of literals that appear in P. So literals of P is just x1, not x2, x3. If we have this notation of vars P, vars plus, vars minus, literals, then in fact P is the AND of all the literals that appear in it. So this notation means take the AND of everything that appears there in the subscript. Alternatively, I could take all the xi's that appear without negation in P and do the AND of them, and all the not xi's that appear with negation in P and do the AND of them. So P equals this AND, or this product, which equals this product and that product. Okay, good. We say that a product is simple if every variable appears at most once in P. So an example of a simple product would be x1 and x2 and not x3. An example of two not simple products are x and x appears twice, and x1 and x2 and not x1. x1 appears twice, once without negation, once with negation. Now, recall that x and not x is a contradiction, namely it is never satisfied. X and x is logically equivalent to x, and not x is also logically equivalent to not x. So this implies that if I'm given a product, I can check the variables that appear in there. If there's a variable that appears both without negation and with negation, then I know that this product is logically equivalent to a contradiction. So it is a contradiction. And if every variable appears always without negations, then I can erase all the instances of x and leave only one. Same thing if it appears with negation always, I can erase all the instances of x of not x except for one, and therefore every product is either a contradiction or logically equivalent to a simple product. Let's define what a minterm is. A simple product, P, is a minterm with respect to the set U of variables if all the variables appear in P. Now, P is simple, so every variable appears in P exactly once, either negated or not negated. So, for example, if U is x, y, z, then the following two products are minterms, x and y and z, not x and not y and z. Now, how many different minterms are there with respect to a set of variables U? So all the variables have to appear in the product, but they can appear either negated or not negated. Right? So think about it. How many different minterms are there with respect to a set, say, of n variables? Okay, I'll leave this as an exercise. Now, I want to state the following lemma. A minterm P attains the truth value 1 for exactly one truth assignment. There's exactly one truth assignment that satisfies P. Let's look, for example, at this minterm, x and y and z. How can a truth assignment over the variables in U satisfy this minterm? Well, every term in the product has to get the value 1 so that the total product gets the value 1. So x must be 1, y must be 1, and z must be 1. So there's exactly one truth assignment over the variables x, y, z that satisfies the minterm x and y and z. What about this minterm, not x and not y and not z? If I want this minterm to be satisfied, I need every literal to be satisfied. So the literal not x is satisfied if the truth value of x is 0. The literal not y is satisfied if the truth value of y is also 0. And the literal z is satisfied if the truth value of z is 1. So the only truth assignment that satisfies not x and not y and z is the truth assignment that assigns 0 to x, 0 to y, and 1 to z. And this is basically the proof of the lemma. Okay? Now I'm ready to define the disjunctive normal form, DNF, also known as sum of products, SOP. So the definition is that a Boolean formula is called the sum of products, or in disjunctive normal form, if it satisfies one of the following conditions. Phi is the OR of k products, where k is greater than or equal to 2. Or phi is just one product. That's also possible. And the case of a single product is like a degenerate case for k equals 1, and it includes the case of a single literal. So phi, which is a single literal or just a variable, is also in DNF. If you look at the parse tree of a formula in DNF, then what you will see is that the parse tree has ors near the root. Below that, it will have subtrees of ands, and the leaves of the ands will be literals. Okay, so if you're interested in how does a parse tree of a formula phi in DNF look like, then it would look like something like this. Let's see some examples of formulas that are in DNF or sum of products. Phi 1, x1 and y, or x and y. So we have two products and an or between them. Phi 2, we have this product, we have this product, we have this product, and we have ors between them. Phi 3 is just a variable, so clearly it is in sum of products form. Now these formulas are not sum of products. X or y and z. You notice that the root here is an and below the and you have an or. So that would disqualify this formula from being a sum of products. Same situation happens in this example. Okay, so now what we want to do is, given a Boolean formula, we want to represent this formula as given a Boolean function, we want to express this Boolean function using a Boolean formula that is a sum of products. So towards this goal, let's define the following definition. Given a binary string v of length n, define the minterm p sub v to be the product of n literals, where the literal li of v is either xi or not xi. So you see the I here is the same as the I here. The V here is the same as the V here. Okay? Good. So when does Li of V equal xi? It equals xi if Vi is 1. If Vi is 0, then Li of V is not xi. Let's see an example. Say V is 0, 1, 1. Then P of V is the product of three literals. The first literal is the negation of x1 because the bit here is 0. The second literal is x2 because the bit here is 1. And the third literal is x3 because the bit here is again 1. Now, what truth assignment satisfies P of V? We know that P of V is a minterm. So we know that it's satisfied by a single truth assignment. What is the truth assignment that satisfies P of V? So that truth assignment would have to satisfy each and every literal in the product. Well, if Vi is 1, then the literal is xi. So to satisfy xi, you must give xi the truth value 1. And if Vi is 0, then in order to satisfy the negation of xi, you need the truth value of xi to be 0. So what we see is that the truth assignment that satisfies P of V is the truth assignment which is induced by V. And we call that truth assignment in the chapter on propositional logic tau sub V. Okay. Now, let's look at this mapping. Given a binary string, we map it to a minterm P of V. Okay, so we have a mapping from binary strings to minterms. Prove that this mapping is a bijection, that it is 1 to 1 and onto from the set of all binary strings to the set of all minterms over the set of variables x1 up to xn. Okay, so I'll leave this as an exercise. Okay, let's define what a preimage is. Given a binary function f from n bits to a single bit, sorry, not a binary function, a Boolean function from n bits to a single bit, let f minus 1 of 1 denote the set of all v's, all the binary strings, such that f of v is 1. Notice that I do not imply here that f is invertible or anything of this sort. Of course it isn't. If n is greater than 1, then The domain is bigger than the range, so the function cannot even be one-to-one. This is just a notation which denotes the pre-image of 1. That means all the arguments, all the v's that are mapped to 1. Okay, that's the pre-image of 1. Good. So, the set of minterms of f is defined as follows. You look at the set of pre-images of 1 with respect to f, and for every vector in which is a pre-image of 1, you look at the minterm which is defined by this binary string. And the set of all such minterms is called the minterms of f. Let's see an example. Suppose I have a Boolean function from 2 bits to 1 bit, and this is the truth table of the function. This is x1, this is x2, this is f of x1, x2, and when x1 and x2 are 0, f of x1, x2 is 0, and so on. When x1 is 0, x2 is 1, f of x1, x2 is 1, and so on. So I have here my truth table. Okay? Now, the pre-image of 1, I look at all the columns here, all the rows in this column in which I have a 1 here, and these rows constitute the pre-image of 1 with respect to this Boolean function. Okay? So, the minterms of f are the minterms that correspond to this row, 0, 1, so I have here 0, 1, and the minterm that corresponds to this row, the 1, 0. Okay? Now, the minterm that corresponds to 0, 1 is the negation of x1 and x2, because x1 has to be negated and x2 is not negated. Let's look at p1, 0. In p1, 0, x1 is 1, so the literal for x1 is without negation, but x2 is 0, so the literal for x2 is with negation. So the set of minterms of f is these two products. Now, I'll leave it as an exercise to check that the OR of these two products expresses the Boolean function f. Okay? Good. So we want to make it into a theorem. Every Boolean function that is not a constant zero function is expressed by the sum of the minterms in the minterms of f. So you take the OR, this sum means OR, you take the OR of all the minterms of f, and that Boolean function that you obtain expresses, that Boolean formula that you obtain expresses the Boolean function f. Okay? Let's prove this theorem. So I want to prove that the OR, the sigma over here denotes OR, that the OR of all the minterms of f express the Boolean function f. So to prove this theorem, I consider a binary string n, and I have two cases. Either f of v is 1 or f of v is 0. If f of v is 1, then I know that p sub v is a minterm of f, because v is in the pre-image of 1. So that means we have already seen that p of v is satisfied by the truth assignment tau v, namely the evaluation of pv with respect to the truth assignment tau v gives us the value 1. And because p of v is satisfied by this truth assignment, then the OR of all these products, which includes p of v is one of the members here in this set, the OR of all these products is also satisfied. So we get that we got a value 1 here, we also get a value 1 here. Now we want to show that if f of v is 0, then the evaluation, this should be a v here, let me make a small correction. The evaluation of this formula with respect to the truth assignment tau of v will give us a 0. Okay, So if f of v is 0, it means that for every minterm in f, every minterm of f is not satisfied by the truth assignment tau of v, right? Because these minterms are satisfied by exactly one truth assignment, and that truth assignment cannot be v. Okay. Therefore, all the p's in this sum have a truth value which is 0, and therefore their OR also has a truth value which is 0. So f of v is 0, and the truth value of the summation of all the p's, where p is a minterm of f, is also 0, and that completes the proof. Okay. Suppose we are interested in short formulas that express a given Boolean function. Okay? Consider the constant Boolean function f that always gets the value 1. Now, the preimage of 1 is the set of all minterms. The number of minterms over n variables is 2 to the n. So the Boolean formula that represents f according to the recipe that we have just described will consist of the sum of all the minterms of this Boolean function, and it will have 2 to the n minterms. On the other hand, this function, which is a constant function, can be represented by a 1. So our method of creating a sum of products formula that expresses f is highly inefficient in this case. So the question of finding shortest sum of products that represents a given Boolean formula is an interesting question, and it is discussed in more detail in our book. Unfortunately, I hate to disappoint you, there is no efficient optimization for this problem. Nobody believes that you can find the shortest representation using sum of products of a given function in an efficient manner. I will elaborate on this in the end of this lecture. Okay, now let's consider the second normal form, which is called CNF, conjunctive normal form, or product of sums. So, instead of products, we have sums, also called occasionally disjunction. A disjunction, or a sum, is simply the OR of literals. Okay? Just as we had with a product which was an AND of literals, here it is an OR of literals. And again, we denote the OR connective either as OR, a plus, or a V, and associativity of the OR, the Boolean function that corresponds to the OR logical connective, allows us to omit the parentheses over here. So we have here examples of sums, x, or not y, or z, and we can replace these connectives with an or with a v, and it's the same thing. And as before, we can define the set of variables that appear in the sum, the positive variables in the sum, the negative variables in the sum, and all the literals in the sum. It should be sum, as in products, yeah? So we could do it with respect to sums as we did it in products. Everything is good. Okay. Now, let's define what a max term is. Okay? So, a sum is simple if every variable appears at most once in S. A simple sum is a max term with respect to a set of variables U if every variable appears exactly once in S, either in negation or not in negation. We have freedom in that, but every variable has to appear. And again, we have the question of how many max terms are there with respect to a set of variables. Now, a max term is satisfied by every truth assignment except for one. In other words, a max term S attains the truth value 0 for exactly one truth assignment. Let's try to see why this is the case. So consider a sum x or not y or z. And we ask ourselves, what should the truth assignment satisfy? What should the truth assignment be so that it does not satisfy this sum? Okay, so if it doesn't satisfy this sum, it means that x has a truth value of 0. Y must have a truth value of 1, so that the negation of y has a truth value of 0. And z again has to have a truth value of 0. So there is exactly one truth assignment for which our sum attains the truth value of 0. Every other truth assignment will satisfy this sum. Okay? We say that a Boolean formula phi is a product of sums, POS, or in conjunctive normal form, CNF, if it satisfies one of the following conditions. Phi is the product. These are ands. It is the product of sums. That's why it's called a product of sums, because we take sums S1 up to Sk, and we take the and of these sums. For the case that k equals 1, it's also good. If phi is just a sum, then everything is also okay, and it is in CNF or POS representation. That would be the degenerate case. Now, recall that dm of phi is the DeMorgan dual of the formula phi. So notice that if P is a product, then the DeMorgan dual of P is a sum, yes? Look at this case, what I drew over here. x1 and x2 and x3, this is a product. I apply the DeMorgan dual, the x1 becomes a negation of x1, the and becomes an or, the x2 becomes negation of x2, and so on. And this is now a sum. So if I start with a product, the DeMorgan dual gives me a sum. Conversely, if I start with a sum, the DeMorgan dual gives me a product. If every variable appears in my product, then every variable appears in the sum. And therefore, if I have a min-term, the DeMorgan dual gives me a max term. Conversely, if I start with a max term, I apply the DeMorgan dual, I get a min-term. Now, let's make it 2 levels. Suppose that P is the sum of products. Then the DeMorgan dual of P is a product of sums, because ands become or, and or becomes and. If P is a product of sums, then the formula DeMorgan dual of P is the sum of products. Indeed, every and becomes an or, and every or becomes an and. Work this out, make sure you understand this observation. Now, what I can do is I can map every binary string to a max term, S of V. So every binary string V, I can map it to a max term, S of V. And S of V is the or of n literals. The n literals are denoted by M1 of V up to Mn of V. And here what I did is I flipped the decision. So if Vi is 0, Mi of V is Xi. If Vi is 1, then Mi of V is not Xi. So you notice that the literal Li of V that I used for the min-term, for the construction of the min-term P sub V, is logically equivalent to the negation of the literal MIV. Okay? So, I look at the max term SV, and I ask which truth assignment does not satisfy SV. Okay? So if it doesn't satisfy SV, what does it mean? Okay, so let's look at Mi of V. I want tau of Mi of V to be 0. Right? Let's put a hat here. That means that if V is 0, then tau hat of Xi has to be 0, because Mi of V equals xi in this case. And if v is 1, vi, sorry. If vi is 1, then tau hat of not xi has to be 0. Namely, tau hat of xi has to be 1. So you see, if I have a 0 here, the truth value of xi has to be 0. If I have a 1 here, the truth value of xi has to be 1. Means that the only truth assignment that does not satisfy SV is the truth assignment tau of v, the truth assignment that corresponds to v. Now, I can take the preimage of 0 with respect to a Boolean function f. So I have a Boolean function f from n bits to 1 bit, and I can take the preimage of 0. And for each preimage of 0, I can take the max term that corresponds to this binary vector. And I call this the set of max terms of f. Okay, so this is our definition of the set of max terms of a function. And the theorem that we want to prove is that every Boolean function that is not the constant 1 is expressed by the AND or the product of the max terms in the set max terms of f. This is the set. Okay? Now, I could prove this theorem directly, as we did in the case of the sum of the minterms and the minterms of f, in order to obtain a sum of products representation. But here we're interested in the product of sums. So I could do this. I could kind of modify the proof so that it would work for this theorem. But let's use DeMorgan duality. Okay. So what is the relation between the minterms of f and the max terms of the negation of f? Negation of f means that if f attains the value 1, negation of f attains the value 0, and vice versa. Okay. So consider the set U of variables x1 up to xn and a function f from n bits to a single bit. And let p denote a minterm with respect to u. Then we claim that p is a minterm of f if and only if the DeMorgan dual of p is a max term of the negation of f. And the same type of theorem is applied with respect to max terms. So if S is a max term of f, then the DeMorgan dual of S is a min term of the negation of f, and vice versa. Okay, so let's try to prove this lemma. So in fact, the proof of the lemma consists of 4 parts. You need to prove implication in one direction, then in the other direction, and then do the same for the second part of the lemma. I'll prove just one implication. So let me prove that if P is a minterm of f, then the DeMorgan dual of P is a max term of the negation of f. Okay? So if P is a minterm of f, it means that there exists a binary string V such that P is the product PV and V is a preimage of 1. So f of V equals 1. Now, if I take P of V and I apply to it a DeMorgan dual, I get exactly the max term S sub V. And we know that the negation of f on V attains the value 0 because f of V attains the value 1. So this means that the DeMorgan dual of P is a max term of the negation of f. And that's what we needed to prove. Okay? So the other cases are proved similarly. Now, we want to prove this theorem, that if you want to obtain a CNF formula that expresses the function f, then what you could do is the following. You can take the negation of f, compute a DNF formula that expresses the negation of f, and apply to this DNF formula a DeMorgan dual. Now we know that the DeMorgan dual of a DNF is a CNF, right? This is a sum of products, and this is a product of sums. So when you do the DeMorgan dual, every OR becomes an AND every AND becomes an OR. So a DNF formula becomes a CNF formula. Okay? Good. So let's prove this theorem. I'll prove it with a sketch. This is not a mathematically rigorous proof, but we've done enough proof, so I think you can complete the details, the missing details. Okay, so given f, let's apply negation to obtain the negation of f. Now let's express the negation of f. So I use this notation to mean let's express the negation of f by a DNF formula. Now, this we know how to do, right? This is the summation of the minterms of negation of f. We have a theorem that tells us what this is. Okay, so let me write this so to make sure that you follow. This is the sum of all the PVs where V is in f minus 1 of 1. Right? This is exactly what this formula is. Now we apply the DeMorgan dual to this formula. Now we know that the DeMorgan dual replaces the formula with a formula which is logically equivalent to its negation, so it's like applying a not. So we get here the DeMorgan dual of the DNF of f. Now we have two negations here. This is the first negation, this is the second negation. So if we have two negations, it means that this f is represented by this formula, and that completes the proof. And this formula is in fact a CNF formula because it's a DeMorgan dual of a DNF formula. Okay, good. Let's stop at this point and continue with the second part of this lecture later.